to everyone. Thank you for attending the live session. And the message in the purple box, I've shown this before. The intent of the materials in the webinar and the files that are available online are for students and faculty only. Oh, there it goes. This is the second course that I am doing for IRIS. The first one I gave half a year ago now, 34 lessons, and there's a web address if you need to locate those. They have the lecture slides, exercise materials, and the webinar recordings, as we are also recording the second course. The second course, Petroleum Exploration, a Field Example, the web address is here as well. There is a total of 8 lectures, and we are combining a couple of them, so it's in a series of 6 webinars. Today we'll do lecture 6 and 7, and then Thursday we'll conclude the series by doing lecture 8. In that G&G in Petroleum Industry course that has the 34 lessons, the things that I'll touch upon today, you can get more information on lesson 10, seal and migration, 13, prospect mapping, 14, prospect risking, 26, direct hydrocarbon indicators, 27, amplitude versus offset, and lesson 30, estimated recovery. So for the first part, we're going to talk about EUR, which is the acronym for estimated ultimate recovery. That's how much volume of oil or gas are we going to get up to the surface. So I'll give a brief overview. We'll talk about the components to doing the analysis, first calculating gross rock volume, then reservoir volume, then pore volume, and then what ultimately we want to have is an estimate of the hydrocarbon volume. So our ultimate goal is to know how much hydrocarbon is in the reservoir and what portion of that we can produce or get up to the surface. And that's what we call the estimated ultimate recovery, or EUR. Our focus is on the amount of hydrocarbon in place. I will talk very briefly about how we go from an in-place volume to what's at the surface. And typically, if we're dealing with oil, we only are able to produce about 15 to 45% of the oil that's in place. And for gas, it can be higher than 45%. So how do we get hydrocarbon in place? And just in case it's not clear, in place means in the reservoir at reservoir conditions. So this is a pictorial outline. We start by estimating the total rock volume, and I'm using a barrel of oil here as an icon. We take that total, and then we have to decide what is reservoir quality, what is non-reservoir quality, and what is not a reservoir at all. So this would be where silts and shales and other lithologies would occur. For that reservoir volume, part of that is the solid grains, so let's say the quartz grains, and then there's the space in between the grains, which are called the pores, and that's where the hydrocarbon and also brine or water will inhabit. And so if we know what the pore volume is, then we have to estimate how much is hydrocarbon. In the diagram, I'm showing it as gas, and how much of it is water. And so what we're after is how much gas or how much oil is in place down in the reservoir. So we first need the total rock volume. What we'll do is we'll try to map out the areal extent of the trap. And all the software that people use these days have a planimeter. You click a polygon, enclose the extent of the hydrocarbon as best you understand it, and it will give you the area in square kilometers or square miles or in acres, whatever units of area you prefer. We have to estimate how far down dip the hydrocarbons extend from the top of the trap. If we're working with seismic that's in two-way travel time, we can get an isochron, a two-way time thickness of the reservoir, and then we can convert that into an isochore thickness in terms of meters or feet, and we do that conversion from time to thickness using some velocity information. And so then we can combine the hydrocarbon extent or area and the thickness, and that will give us a total rock volume. So on the right, we have the field area. We multiply that by an average thickness. We get the total rock volume. Given the total rock volume, then we need to estimate the net to gross for the reservoir interval. So how much is good sands, reservoir quality sands that we can get the fluids out of versus everything else that we use the term waste rock. If you've been employed and you get your paycheck, you know that there's a net amount and a gross amount. The net is what you get paid in theory, but then they take out your taxes and your medical and this and that and the other thing, and the gross is what you actually get the check written for and that you can deposit in the bank. Net to gross often varies by the environment of deposition for the reservoir unit. And so for Barracouta, if you do the associated exercise, we'll use a net to gross if it's in a delta front environment of 80%, where we have storms and waves cleaning things up and winnowing out the finer materials. If it's in a delta plain environment, we use a net to gross of 65%. And if it's in a fluvial environment, then we use a net to gross of 50%. And if you were with us last Thursday, we talked about these three different depositional environments, and the exercise had you do some mapping of how these environments varied across the field and as we went into deeper portions of the reservoir interval. So if we have the total rock volume, we multiply it by the net to gross, and that will give us our reservoir rock volume. So if we have the reservoir rock volume, the next thing we want is the pore volume. And so we use a parameter, a rock parameter called porosity, and that's the percentage of the total volume that's represented by the pore space, or the space in between the solid grains. Porosity also varies by the depositional environment. And for Barracouta, if we're in a delta front environment, our porosity we're going to assume is around 20%. If it's delta plain, it's about 18%. And if it's in a fluvial environment, it's about 16%. The cleaner the sands, the higher the porosity tends to be. So the next thing is to get the hydrocarbon volume. We start with the net pore volume. And then there's a parameter called the hydrocarbon saturation. And that means what percentage of the pore space is filled with hydrocarbon, oil or gas. The rest of it will be filled with what is called irreducible water. Usually it's going to be a salty water, so a brine. And that's the water that the hydrocarbon, as it moved into the reservoir, just couldn't elbow its way in to force all the water out. So hydrocarbon saturation can vary quite a bit. For the Barracouta field, we'll assume a hydrocarbon saturation of about 90%, which is on kind of a high side worldwide, but the Barracouta field, the reservoir has very good permeability, and so good connectiveness of the pore space, and hence the hydrocarbon has replaced 90% of the pore space with hydrocarbon. The other things that we need to worry about, or let me go back one slide. So we take the net volume, we multiply hydrocarbon saturation, and that gives me the hydrocarbon volume in place at reservoir conditions, at reservoir depth, at reservoir temperature, at reservoir pressure. Now, the other thing we need in order to get the EUR at the surface are two things. One, how much of the hydrocarbon in the rock can we actually get out? And we call that the recovery efficiency. And then as we take the hydrocarbons from depth under higher temperatures and pressures, we bring it up to the surface. And here I have a drilling rig as a little image. The hydrocarbon is going to get cooler and it's going to become under less and less pressure. And as the temperature decreases and the pressure decreases, the hydrocarbons will expand. And so there's an expansion factor that we have to include. The expansion factor for gas is much higher than the expansion factor for oil. So if you do the exercise, we're going to assume a recovery efficiency of around 70%. And the expansion factor for gas at Barracouta, I talked to some SO engineers before I retired, and they use a number of 111. So 111 cubic meters, I'm sorry, 1 cubic meter in the reservoir, by the time we bring it up to the surface, will expand to be 111 cubic meters. So I've mentioned the exercise 6. It's determining the EUR, estimated ultimate recovery for Barracouta. And so I have an exercise that will lead you through the steps that you need to take. You'll do some calculations, figuring out the total rock volume, and then whittling it down till you get to the hydrocarbon in place. And then I give you a recovery efficiency and an expansion factor, and so you can estimate what the amount of hydrocarbon volume, gas volume, you'll have at the surface. So Max, why don't we pause for a minute or so and see if there are any questions on EUR before we proceed.
Nothing so far.
Okay. If you are new to the webinar series, there should be a GoToWebinar control panel, and there's a section that has chat, and you can type some questions in there. They will appear on Max's computer, and then he can read them to me, and I can try to answer them. So let's move on to Lecture 7, Maturing a Lead and doing assessment and risking. And so to mature a prospect, what we have to do is we have to define the prospect elements, and we've done that thus far for Barracouta, source, reservoir, trap, seal, migration. We need to estimate the hydrocarbon volumes, and the exercise 6 on EUR does that. The three other things we worry about is, well, what type of hydrocarbon will we anticipate bringing up to the surface? Will it be gas, or will it be oil, or will it be oil with gas, or gas with oil? We have to do an assessment to figure out how much we might be able to recover, and then we have to do a risk analysis. How certain are we that everything is going to work as we hope, and that we'll have an economic discovery? So this lecture, Lecture 7, we'll talk about hydrocarbon type, assessment, and risk. So for the type of hydrocarbon, is it going to be oil, or is it going to be gas, or is it going to be some of each? There's two approaches. One is qualitative, and I'll talk about that with this first bullet point. And then there's also a quantitative approach, which I'll talk about in a minute or so. So from our basin modeling, we've built the present-day basin architecture, the horizons and faults and ages, lithologies. We can backstrip it and then model it forward through time. And we can analyze the hydrocarbon systems. We can think about reservoir and how that reservoir properties have changed from time of deposition. We can think about source and how much it might have generated from time of deposition. We can think about seal and migration and trap formation. So doing all of that, we may be able to get a good handle on the type of fluid that we expect. Some of that depends on the organic matter type in our source. Some of it depends on our temperature history, whether our source has been only in the oil window, if it's been in the oil and the gas window. If it's never gotten into the oil window, then we may expect that we don't have any hydrocarbon because it just didn't get cooked. So we want to think about, consider what did the source generate over geological time, and that would be the source within the fetch area for our prospect. And we also have to worry about, did the trap leak, or was there hydrocarbon spillage from one trap to another? And I'll talk a little bit more about that in a few minutes. And then we can do a quantitative analysis where instead of being somewhat fuzzy on the numbers, we try to be more careful with our numbers. There may be something in the seismic response that is an indication that we do have hydrocarbons. We call those direct hydrocarbon indicators, DHIs. And in the overall category of DHIs, there is amplitude versus offset, which is AVO. And if we're in a basin where AVO is effective, we can differentiate where we would think we would have oil trapped, where we would have gas trapped, and where we would have no hydrocarbons trapped. And if we think the geophysics works out such that hydrocarbons do give us a measurable change, then we can do things like extracting seismic amplitudes from a near stack and a far stack and try to quantify what the likelihood is that a trap would hold oil versus gas versus brine. So with the qualitative analysis, we model and compare the volume of oil and gas that's generated by the source within the fetch area and compare that with the trap volume. We can analyze how the trap might be filled with oil, how it might be filled with gas. We have to consider, has some of the hydrocarbon been spilling out of one of the traps, and where might spilled hydrocarbons end up if we have spillage from deeper traps into shallower traps. So hydrocarbon migration, I think I talked about this a little bit earlier in this series. Again, you can go to the first series of 34 lectures, and there's material on hydrocarbon migration there. The migration process is controlled by buoyancy. And so I have a little diagram of a cross-section. I have a carrier bed, so you think porous and permeable. I have a source bed where I have hydrocarbon organic matter percentage and organic matter type. If I generate a drop of oil within the source, it's going to, through buoyancy, try to get to a higher location, the lower pressure location. So it will migrate out of the source rock, and we call that primary migration. And then it will continue to move up and up and up until it gets to a more porous and permeable layer. And if the layer above the yellow is a bit less permeable, it forms somewhat of a seal, then we will get lateral migration up dip or up the pressure gradient to a culmination or a trap or a high point on a syncline, on an anticline. So let's consider this where we have an anticline at this location. We'll call it trap W for west. We have another anticline, trap E for east. If we generate some oil here, it will percolate up and then travel to the top of the trap. It will move to the top of trap W. If we have oil that's generated here, again, it will percolate and move up dip to trap E. But what happens if we generate some oil here? It percolates up and it gets to this point which is the deepest part of the syncline, there's a 50% chance it will move west and a 50% chance that it will move east. So we call this a drainage divide, and this would separate the the fetch area for trap W from the fetch area from trap E. And so we're always looking for where these synclinal low points might be that form our boundaries separating which direction hydrocarbons will migrate. So here I have a little diagram of a 3D view. We have an anticline here, another one here, a third one, a fourth one, and maybe a fifth one here. The blue would be these deeps within the synclines that become our drainage divides. They define the fetch for this trap, another fetch for this trap, and this trap, and this trap, and this trap. And then on the diagram, I'm showing some trapped hydrocarbon. The red or pink is the gas, the green is the oil. And the black arrows are flow diagrams to show from several select points the path I think hydrocarbons would migrate to reach those traps. Instead of a 3D block image, I can superimpose that on a flat map. And so what I would again see is the blue drainage divides, or the axes of the lows. I have the high points or the culminations, or where the hydrocarbons will collect. And again, I can show some a few hypothetical paths of the hydrocarbon migration. So we can use seismic. Let me go back a second. Oops. Yeah. So we can look at our carrier bed, which might also be our reservoir interval. We can do this type of an analysis and try to figure out how much was generated within this fetch area, feeding gas and oil to this high, how much was generated in this fetch area, leading to migration of oil and gas to this high. Now we can be more quantitative if we can use our seismic and maybe boost our confidence that we have hydrocarbon and what type it is and how much fill a particular trap has. We can look for and use DHIs, which are direct hydrocarbon indicators. Seismic DHIs are anomalous seismic responses that are caused by the presence of hydrocarbons within the porous and permeable rock. And so a reservoir quality sand with brine in it will have different acoustic properties than the same sand with oil in it, and that will be different from the same sand with gas in it. Sometimes those differences are large enough that we can detect and measure those differences, and that's what can build our confidence. And so we're always worried about or concerned about or thinking about, are the changes due to the presence of hydrocarbon going to be seismically detectable given our data set, our data quality, the way it was acquired, the way the seismic was processed. So DHIs display one or more types of characteristics that are consistent with hydrocarbons being within the rock matrix. So here is a list of hydrocarbon indicators. There's 1, 2, 3, 4, 5, 6, 7 that we'll look at. There's some other indicators that I'll mention in a moment. The most common hydrocarbon indicator is amplitude strength. And so here we have some seismic. The black and white wiggles are the real seismic. The red is a modeled or synthetic seismic trace based on a well. And you can see that in this portion, we have a really strong trough or swing to the left. And then we have a really strong black or really high swing to the right. And these amplitudes are much higher because the impedance contrast of a hydrocarbon sand is larger than the impedance contrast of the same sand when it has water in it. So if we have a very anomalous amplitude, that can be an indicator that we have hydrocarbons present. Impedance signature is another hydrocarbon indicator. The image on the upper right is the regular reflection seismic data. We can use processing, fairly high-end processing, to go from seismic reflection amplitude strength to an estimate of what the impedance is. And the higher impedances are the greens, the lower impedances are the oranges and red. And so we see here an anomaly. We see low impedance that's embedded within higher impedance. So we see red encased by green. We also see red encased by green here. Hydrocarbons usually lower the impedance of the rocks. And so if we're looking for evidence of hydrocarbon, what we would tend to look for is evidence for low impedance if, in fact, we have a seismic impedance volume. Those are fairly rare, although they're becoming more commonplace. The other hydrocarbon indicator, or the next one, is amplitude versus offset. And so that is where we have the right rock properties and acoustic properties, so that at the top of the reservoir, if we look at rays that have a low angle of incidence, we call those near angles, we get a slightly different amplitude response than we have when we have higher angles of incidence or reflection, and those we call far angle stacks. And so you can see in this example, the top of the reservoir has a moderate trough, the base has a moderate peak, but if we look at the far angle, we have a much larger trough and a much larger peak. We have the amplitudes of the troughs and peaks increasing as we go from near to far, and so that's a AVO response, and that particular response we classify as a type 3 response. If you look at the lecture on AVO in the 34 lecture series, it'll have more information on that. And then there are several seismic pieces of evidence that we can gather that tells us that we may have a fluid contact. The first of which is a flat spot. And so here the top of the reservoir unit is in this dark blue. We can see a higher amplitude, a darker red up here, a lighter red or orange down here. But we also see this black that's kind of cutting across the stratigraphy that's dipping down to the right. This almost flat event is a fluid contact because the sands above it with hydrocarbon in it have a different acoustic impedance than the sands below it with water. And so we actually can generate a reflection off of the change in fluids. The fluid contact will be flat in depth. However, if we're looking at two-way time seismic data, it may not be perfectly flat because of some variations in velocities above the location where we see this flat spot. Another thing that indicates a fluid contact is a polarity reversal. And so here, this example from Alistair Brown's book, the top of the reservoir is a black or a peak, and it transitions into a red or a trough. And the base of the reservoir is yellow, and it transitions into a black. And so the acoustic properties may be such that I get one type of impedance contrast where there's hydrocarbon. Usually it indicates a drop in impedance, and then I get a different response, which is an increase in impedance. And it could just so happen that the polarity flips depending on the rock properties and the fluid properties. The third type of fluid contact is an abrupt down dip termination. So again, here's an example. Blue is the top of the reservoir. Higher amplitudes up here, dimmer amplitudes here. And this really bright orange all of a sudden stops, and this black all of a sudden stops. And you can, I can't remember if I have an animation, but you can almost draw a line through here. There it is. That is a seismic indication, evidence that there may be a fluid contact. And this piece of seismic actually comes from the Barracouta field. And then with a fluid contact, we should see a good fit of the seismic anomaly to the structure. This is from the Gulf of Mexico. We have seismic amplitudes. The higher amplitudes are the hotter colors. The lower amplitudes are the cooler colors, the blues. And the hydrocarbon contact known from the wells is shown in black here and in black here. And you can see how the higher amplitudes, the yellows, orange, and reds, are all above that particular contour, and the moderate amplitudes, the blues, tend to be below it. And so if we look at just where the amplitudes are anomalously high, it matches quite well with the extent of the hydrocarbon, the contact between hydrocarbon, I think this might be gas to water, that we know from the field given the well data. There are some other indicators I don't have time to go into. There's things called seismic chimneys. We also look for sags or pull-ups of reflectors associated with velocity differences when we have and when we do not have hydrocarbon. And we also can see attenuation of higher frequencies as a suggestion that we may have a hydrocarbon effect going on. Let me talk a little bit about AVO a little more. What we can do is we can look at a gather that shows us the seismic response as a function of either offset or reflection angle. So this would be low angle or near offset. This would be higher reflection angle or far offset. We see this trough, and as we go from near to far, we see that it's hardly a deflection to the left to a moderate to a high deflection to the left. So we can plot for this red horizon marking that trough the amplitude for each of the traces. It looks like I have about 10 traces here, so that would be 10-fold data. I should then have 10 points on my amplitude versus offset. What we'll do is we'll draw a straight line that is a best fit to that scatter of data, and that straight line would have an intercept where it intercepts 0, and it would have a slope. What's the slope of that line? I can then use a cross plot looking at the intercept plotted against the gradient or the slope, and for this straight line best fit, that might give me a point here, a negative intercept, so it's below 0, and a negative slope dipping down to the right. If I do the same thing, but the reservoir, instead of having gas, has oil in it, it would plot here. And if it had water in it, it would plot here on this intercept versus gradient cross plot. And so this is a case where the rock properties are just right that we can get a good detectable AVO response. So we can do modeling. We can look at the browns would be shales, and the colors are sands. The red is a gas-filled sand. The green is an oil-filled sand. The blue is a water-filled sand. The first column, we have 10% porosity in the sands, 20% porosity, and 30% porosity. And so we can use equations, geophysics or rock physics, in order to calculate what sort of responses we would expect at the shale into the sand boundary. And so again, this is near angle or near offset to far angle or far offset. This is the gas at 10%, at 20%, at 30%, the oil at the 3 porosities, and the water at the 3 porosities. If we plot that on AVO cross space, the 10% gas is here, the 10% porosity oil, 10% brine, 20%, and 30%. The diagonal dashed magenta line is the response we would expect to see if we had shale on shale. And so, I'm sorry, went a little too fast. So we can quantify how far off of the magenta line the AVO intercept cross plot is, and that can help us indicate whether it should be gas or oil or brine, and whether it's going to be closer to 10% porosity or 20% porosity or 30% porosity. Where AVO works, we talk about them being Goldilocks basins because the rock and fluid properties are just right that we can detect changes associated with both porosity and hydrocarbon or fluid type. So I'm going to use a hypothetical example of two prospects, the alpha prospect and the beta prospect. We have a fault here and a fault here, and this is the high point getting deeper, then the fault steps up, the high point and getting deeper. So the question is, should we drill the alpha high? Should we drill the beta high? Should we drill both of them? If so, in what order? Should we only drill one of them, or should we not drill either of them? This is a seismic line across the alpha prospect. So here's the fault down to the right. Magenta is the top of the reservoir, and purple is the base of the reservoir. So we can model the area and look at how the cross-section may have looked at different points in the past. So 18 million years ago, this is my source interval in the kind of pale blue. My reservoir and my migration route interval is in yellow, and then the light green is the seal. We have a certain amount of water depth that we've interpreted, and this is where one fault is going to develop, and this is where the second fault is going to develop. My geochemists tell me that the source in this area is cooked enough that I'm generating only oil. And so I have a region to the west of alpha where I have an oil kitchen, and that oil would migrate, hit the seal, and then move up the porous permeable migration pathway, and then start to fill the anticline here at alpha. If I generate more oil than that alpha high will hold, then it could spill and I could start to fill beta. Now let's go forward in geological time. This is our reconstruction 10 million years ago. We now have generation in the low to the west of beta. We have generation in the low continuing in the to the west of alpha. We have oil generation in both cases, and we have oil migrating and starting to fill alpha. For the time being, let me assume that the alpha fault seals, so the hydrocarbons are going to be trapped there. The oil generated to the, let's call this the beta syncline, will move up dip and be trapped here. Again, I'll assume that for the time being, at least, this fault also is sealing. And then if I go to the present day, now I have the source in the alpha syncline generating oil and generating gas. The source in the beta syncline is just generating oil. So the oil migrates and continues to add volume to the trap at beta. I have gas and oil reaching alpha. So I model or suspect or predict that I'll have a gas cap and an oil leg. So in map view, this is how the area might have looked 18 million years ago. The faults have not started. I'd have oil in the culmination at alpha, and if I had some spillage, I might be able to get some oil into beta. 10 million years ago, now both faults are in place, and I'm going to assume the faults seal. Generation of oil in the alpha low allows me to accumulate and trap a fair amount of oil. Oil generated in the beta low has allowed oil to generate, migrate, and be trapped in the beta anticline. And then present day, my prediction is that I'll have a gas cap and an oil leg at alpha. I'll just have oil, maybe a minor amount of gas in beta. So this is our most likely scenario for present day, a gas cap and an oil leg at alpha, a certain volume of oil, a certain volume of gas, and then at beta, mostly oil, and I could figure out what the most likely volume would be. Many times, seismic may give us clues as to if this scenario is correct or not. So perhaps we can use seismic to verify this scenario, which is largely based on basin modeling and generation and trap formation. It may be able to tell us with the seismic what level the traps are filled, and we can then estimate a value in terms of dollars for this scenario. And we could also consider what happens if there's more hydrocarbons, what happens if there are less. And I have to also ask, how risky is it that this prospect is going to be as this most likely scenario depicts? So here's that seismic line across alpha. If I look more carefully at the seismic amplitudes within the reservoir zone, there seems to be a change from moderate to low amplitudes, and it looks like there might be almost a flat boundary separating that. And so that might be a fluid contact. And so that's good news if it is, because it tells me I have a change in fluid, probably brine down here, and then oil or gas up here. But if I look at the amplitudes a little further, I go from really strong to moderate. This is a little bit more interpretive, a little bit more optimistic, but there may be a fluid contact here as well. If that's the case, because gas is less dense than oil, I would have gas in this part of the reservoir, I would have oil between the dotted red and the dotted blue, and then I'd have brine further down. So if there are two fluid contacts, it gives me a good handle on how far down dip the gas is, and then I can calculate this volume and get the recovery amount for the gas. And I would have this portion of the trap filled with oil, and again, I could calculate the recoverable oil. So let me move on then to assessment. And assessment is where we try to quantify how much we think we're going to have. There are two types of assessment that we can do. One is deterministic, the other is probabilistic. So with deterministic, we assign one value for each of the parameters that we need, and we need parameters such as net to gross and porosity and area of the field and average thickness of the field. We give one value to all the parameters. There's probably 20 parameters. We do the calculation and we come up with one number. So in this case, 20 MBO is million barrels of oil. Probabilistic assessment, what we do is we give it a range of values for each of the 20 or so parameters, and then we'll get a range of outcomes. We'll get a mean value, maybe 20 million or 200 million, I'm sorry. But we might also say it could be plus or minus 50 million barrels. So in a deterministic assessment, we might say that the reservoir extends over 18.5 kilometers. It has an average thickness of 100 meters. And so that gives me a gross rock volume. We give it a most likely net to gross and porosity and hydrocarbon saturation and formation volume factor. This is another way to express the expansion factor. And so that will give me an estimate with these numbers that I have 960 million barrels in place. We might assign a certain recovery efficiency. And so we might say we expect to recover 320 million barrels. We say this is an unrisked value or volume because it assumes that everything works. We'll talk about how we go from unrisked to risk in about 2 minutes here. So with alpha in my little example we had, we might say, well, there's 4 main possibilities that we can envision. One is that we have a gas cap in an oil leg, and maybe we say there's a 45% chance that this is the right picture. There might be only gas in the reservoir, and maybe we say there's a 25% chance that this is the correct picture. The third possibility is we only have one fluid, but it's all oil, and maybe we estimate that has a 20% chance of occurrence. And the fourth possibility is that the reservoir might be filled with a low percentage of gas. So it might be 10% gas and 90% brine. We call that low gas saturation. It will give a very similar seismic response as gas only, so it's hard to differentiate these two. And so we always have to consider, what if it's low gas saturation? So if you work through the numbers for alpha and beta, we have an area of volume, area and thickness gives us a volume. We work down, we work down, we work down. We come up with 320 million barrels in alpha, 146 million barrels in beta. And these are the unrisked numbers. So the next step is, how can we get what is more meaningful and more likely or real world? What's the risk values? So for alpha, I said there were 4 scenarios, and these are the numbers that I calculate. If it's low gas, there's no oil and there's no recoverable gas, there wouldn't be enough to make money off of. If it's oil only, 320. If it's gas only, 440 billion cubic feet. And we can convert that into oil equivalent barrels. If in this area we needed 100 million barrels equivalent in order to make it economic, we have more than 100 here. We don't have 100 here, so this would be non-economic. We have 320, more than 100 here, so this we would make money off of, and this certainly we wouldn't make money off of. So this is the type of analysis that explorationists would go through to get the prospect ready to present to management. So with the probabilistic assessment, what we usually do is we assign a range. So for the area, the most likely it might be 20 square kilometers, but it could be as low as 12 or it could be as high as 27. For all of the other parameters, thickness and net gross and porosity, hydrocarbon saturation, formation volume factor or expansion factor, recovery efficiency, we give a most likely, a min, and a max. And then we can calculate using a Monte Carlo method. Fortunately, the computer software does it for us. We could do 1,000 simulations or 2,000 or 1,000,000. Usually people run about 1,000. And then they report the results as an exceedance probability. And to read this, we would say that there is a 100% chance of having no oil or more. 100 million is the economic minimum, so we would say there's about a 73% chance that there'd be 100 million barrels or more. There's a 5% chance that we would have 325 million barrels or more. The 50% is right here, so the mean value, 50% chance to find 200 million barrels or more, and there's a 75% chance of finding at least the economic minimum. So the last item we worry about is risk. How confident are we? And so some people talk about risk. Our prospect might have a 25% risk, or other people talk about chance of success. My prospect has a 75% chance of success. Another way to think about this is if I had 4 very similar prospects and they all risked about the same, in this case, 1 out of 4 would work, and that's the risk, or no, I'm sorry, 1 out of 4 would fail, and that would be the risk. 3 out of 4 would succeed, and that's the chance of success. So the thing you have to do is figure out what type of number does your management normally deal with. Is it risk, and you want the risk to be low, or is it chance of success, and you want the chance of success number to be high? To get the risk, what we look at are factors such as these. There's 9 on this slide: source quality, reservoir presence, trap quality, source maturity, reservoir quality, seal adequacy, hydrocarbon migration, biodegradation or the lack thereof, and a chance that it is not low gas saturation. So a team of experts will look at the key elements, and they'll give each of these 9 factors a score between 0 and 1, and then you multiply those all together, and you come up with a chance of success. So for alpha, the biggest risk is seal adequacy. Was that fault sealing, or did it allow hydrocarbons to partially leak out or all of the hydrocarbons to leak out? And then we had a 10% chance that it could be low gas saturation. If we multiply these 9 numbers together, we come up with a chance of success for alpha of 72%. So that's how we try to deal with the uncertainty and the either risk or chance of success. We can go back to that exceedance probability. Before it was 100%. Now, because our chance of success is 72, we rescale it so that 0 is at 72%, and then we can look at the exceedance probability. And because we have 4 scenarios, we can actually identify them. This is the gas-only case. This is the gas cap and the oil leg, and this is the oil-only case. And low gas saturation doesn't appear on here because we wouldn't find anything that was economic. Our economic minimum is 100 million barrels. And so now with the risking, the rescaling it to 72% for 0, now we have about a 58% chance of finding economic minimum or not. So that's the type of analysis. Those are the types of numbers that managers are interested in. So the 50% case here is about 240 million barrels, but there's a 10% chance that we could have 350 million barrels. So those are the numbers that management will want to know, and then they'll chew on those numbers and they'll decide, yes, we'll take a chance and we'll drill alpha, or no, we think we have better ways we can spend our money where we can get more volume with less risk. Exercise 7, you'll go through one of these chance of success analyses, and I have about 4 minutes left. So Max, if we have a couple of questions, we can still finish at the top of the hour.
Yeah, no questions posted so far. I was curious, what's the threshold for the Goldilocks zone?
The Goldilocks, that varies based on the basin and the age of the rocks and the temperatures and the pressures. So there's not a simple formula that you can use. But either a geophysicist or a rock physicist can do some analyses depending on where you are exploring, and they can tell you whether or not AVO should work, and if we could use things like amplitude strength to try to differentiate oil from gas from brine. Okay. So our last webinar, I should have moved this down. Our Our last webinar is on Thursday of this week. The topic is management review. I am going to pull all of the material that we covered and the exercise material and start out with some comments about what type of information you want to present. And then I'll show, using Barracouta, how I might present the Barracouta prospect to my management in the hopes that they give me a green light to go ahead and drill the prospect. So that should be a very informative webinar.
All right. Well, thank you, Fred. We'll see you all.
Okay. Well, thanks everyone for watching, either live or via the video, and wish you all a wonderful day and great success if you become an explorer like me.
That's right. Thank you, Fred, and we'll see you all Thursday for the last webinar.
Okay. Thank you, Max.